I'm Alex Sanchez. I think Cam already mentioned some of this stuff, right? He mentioned the energy equation and friction slopes and things like that. Okay, so you guys got a little bit of an introduction to this. Hopefully it won't be so heavy. So what we're going to cover is some basic open channel flow concepts, kind of review of, undergrad, the stuff you guys saw, energy principles, how the cross-section is subdivided into bins and conveyance is computed for each bin and then summed and those things. The computational procedure, so how do we solve for water levels, right? And then some details like how critical depth is computed, the momentum equation. There's certain situations when we don't use the energy equation and we use the momentum equation. Talk about that a little bit. We're going to cover more of this later during the week when we talk about mixed flow. We're only going to introduce that today. And then talk a little bit about cross-section spacing. There was a few questions about that during the workshop today when people were drawing the cross-sections. And then at the end, some limitations about 1D modeling. When do you want to do 1D modeling, specifically steady flow? That's what we're covering this week, versus unsteady 1D or unsteady 2D, right? So open channel flow, right? There's two main kinds of open channel flow. There's steady flow and unsteady. Obviously, people know this, that steady flow is when the conditions are not changing, your water levels are not changing, everything's kind of static in time, and unsteady, the variables, your state variables, other variables are changing in time. And then you have uniform flow versus varied flow. Uniform flow means that things are uniform in the downstream and upstream directions. Your depths are the same, your hydraulic radius, all other variables are uniform in the longitudinal direction, and whereas varied flow, your variables are changing downstream. And when you have varied flow, you can have rapidly varied flow or gradually varied flow. Gradually varied flow is just, it is what it sounds like. Things are changing more slowly, more gradually, and rapidly varied flow, usually like control structures like weirs and things like that, your flow will change more rapidly. Yeah. An important parameter that we're going to talk about, bring up a lot during this week, is this Froude number. And it's a parameter, a non-dimensional parameter that tells you whether the flow is supercritical or not. It's also, you can think of it as the ratio between the inertial and gravitational forces. And so what is the Froude number a function of, really, right? It's only discharge, right? Because here you have the square root of GD, and up here you have the velocity. So it's only a function of the discharge and, ignoring gravity. And if you remember, this bottom part here is the celerity, the long wave celerity, right? So it's just a ratio of how fast the current is moving over how fast the maximum wave speed could be under those conditions. This is a flume experiment where there's gradually varied flow and then there's a hydraulic jump. And it happens over several cross sections. This is rapidly varied flow, and this is gradually varied flow here. Yeah, and we'll talk more about mixed flow later during the week. Yeah, velocity distribution. This is important because it affects your energy losses. If you have higher or lower flows in different parts of your cross section, that produces different losses because you have more dissipation in a high flow over a shallow depth than you do in a high flow over a deep depth, right? We're going to show how the friction is computed later on, but you'll see that it's a function of the water depth, right? So your velocity distribution, even for the same flow, if you have a different velocity distribution, you'll have different energy losses in that cross section. So that's why it's important. And obviously, for real life, also, different parts of your cross section are going to have different roughnesses, and so that will lead to different losses. The flow distribution is also important for other things because for computing a reach length, that's flow weighted. So different velocity distribution over a cross section is going to lead to a different reach length, right? In between cross sections. And we'll talk about some of the parameters that we compute as a function of the flow distribution during this talk and throughout the week. So it's important. This is an example of what an actual flow distribution would look like. This RAS is 1D, right? So you would have to consider what the real flow distribution would look like in subdividing your channel into bins for the conveyance calculation, right? You want to look at the natural breaks in the cross section, and then or changes in roughness to distribute your bins for the cross sections. This is one of the parameters, alpha, that we utilize. So this is the kinetic energy head, the v squared over 2g, right? And because the cross section is going to have a velocity distribution, so this is going to have, in general, like a very different velocity from this overbank area here. So it's subdivided into two sections with assumed constant velocities in those. And then if you want to compute an average kinetic energy for the cross section, then you need to introduce this alpha parameter, right? And then I'll show in the next slide how to calculate that. So it's derived this way, where you just add the two components together with that's flow weighted, right? You add those two together using a flow weighting, and then you can back out how to compute it without actually knowing the flows, just with the conveyance and the area for each section. That's how a RAS computes that alpha parameter that's used to compute the kinetic energy head. This is the energy equation that Cam already talked to you guys about earlier this week. So you have the z's are the bed elevations, the y's are the depths, and then this is a kinetic energy head, and it's just a balance, right? This energy head has to be equal to this energy head plus the energy losses is h sub e, right? Those are all the energy losses due to friction and turbulence and contraction and expansion, everything. The two main components are these, right? The friction losses, and these are contraction and expansions. Where's turbulence in here? It's lumped here in the Manning's N in this friction loss. It's lumped in that term. The flow weighted reach length. So this is another reason why the velocity distribution is important, because different distributions will give you a different reach length. And what is this one used for? It's here. So the longer your reach length, the more friction losses you're going to have. All right, so conveyance. How do you define conveyance? Well, this is one way of defining it, right? Where this is your friction slope, your flow, and then your conveyance you can define that way. If we utilize Manning's equation, which is this equation here, then you can back out what your conveyance definition is. And this, if you use a different roughness parameter like chassis or roughness height or something, you would get a different formula for the conveyance. What are the units for conveyance? It's the units of the discharge, right? Because this is a slope. So for a cross-section, how does RAS compute the conveyance, the total conveyance for a cross-section? How does it subdivide that cross-section? The default way is to have a left overbank, a channel, and a right overbank. Each one of those segments can be subdivided into smaller components, and that's what is shown here, right? This left overbank is actually subdivided into two conveyance components, right? Those two get added into a left overbank. The channel is one segment, and then the right overbank is one, but it could be split into multiple. What decides that is what the user specifies for the end value, right? So if you remember the cross-section editor, it had the station elevation data, and you can also specify the Manning's N, right? And so every time you specify Manning's N, you're subdividing that part of your cross-section into more portions. So this is an example where, because there's a break here, right, the velocity in this section is going to be very different from here, because it's just the geometry, right? You're going to have a higher velocity here than you are here. So even though your roughness is the same for those, let's say, you still want to go in and put another Manning's N value to kind of divide that part of your cross-section, so that you can have one conveyance here and a separate conveyance there, right? So follow the kind of the terrain of your cross-sections and guiding you. Let that guide you in determining where to break up your cross-section into conveyance components. Because of the steep banks of the channel, it's better to have a composite Manning's N value for the channel if you have variable roughness along the channel, because if you divided this into sub-bins, the bins that are in on the banks, those would get a lot of wetted perimeter, and therefore a lot of friction assigned to those. And that's not really realistic, right? It's more realistic to assume a constant velocity for the whole channel and compute a a composite Manning's N value, even if it's varying along that channel. This is how we compute it, that composite Manning's N value inside the channel. So the overbanks, you can divide them if you have variable Manning's N, and it splits it up into smaller conveyance components, right? But the channel, it doesn't. If you have variable roughness inside the channel, it's going to compute a composite Manning's N for the channel and compute only one conveyance component. So friction, I mentioned this, the friction losses here, the length and this friction slope. This is how the energy slope gets computed. K gets computed with Manning's equation. I showed that earlier. Friction slope, there's many ways of computing that friction slope because it, at least 1D steady flow and 1D unsteady need an average friction slope between cross sections because the energy losses, the friction losses are computed between cross sections, right? So how do you compute that friction slope between cross sections? Well, there's many ways. The default way is this average conveyance approach that's shown here, but that's just the default. There's these other options that you can go in and experiment with. Okay, computation procedure. So for normal subcritical flow, we start from the downstream end and go upstream, right? So given a stage downstream, we're going to compute water surfaces in the upstream direction, but it's you have to use an iterative procedure because you have to guess what the upstream water level is going to be, compute the hydraulic properties like conveyance and all of those, and then compute the friction slope that we just showed, right? Compute energy losses and then check if that was an okay or if that guessed water surface was accurate. So this is a computation procedure for solving the steady flow, right? For how to get the water surfaces. Starting from downstream, you guess a water surface, and then you compute the conveyance and all the other variables, right? The area and such. Compute the average friction slope between the cross sections, and then you can solve that energy equation, right? The Bernoulli equation. And then you compare your guessed water level with this newly computed one from the energy equation. And if they're within a certain tolerance, the default is 0.01 and you can change this, then it says, okay, I've converged. If they're different, if they're larger than that difference, then it'll keep iterating until it's converged. And there's a maximum number of 20 iterations, and you can change that. If it doesn't converge, then it'll use the best solution during the iteration process. And by best, I mean the one with the lowest error. And then if the error is really too large, larger than a tolerance of like 0.3 feet, then it'll say, okay, I wasn't able to get a reasonable solution. I'm just going to use critical depth. Each time it guesses a water surface, so that first step of the previous slide, this is how it does it. The first time it says, okay, I'm just going to assume my depth is constant, going upstream, and it projects the water surface upstream. The second guess is done this way, and then, after that it does the secant method. So it uses the errors of previous iterations to kind of predict what a better water surface guess is going to be. If the secant method fails, it can fail because there's a denominator with an error in it. If that error gets really small, then the secant method can blow up and not converge. If it fails, then it'll use this method to get a new guess for the water surface. So this is about that first step, right? That guess at the beginning of each iteration. Yeah, I mentioned these tolerances. If it doesn't converge within 20 trials, it'll use critical depth. So the minimum error is associated with the best guess of the water surface during the 20 trials. Okay, critical depth is computed at any cross-section under these conditions, right? If the method didn't converge after 20 iterations or whatever the user specified, then it says, okay, I need to compute critical depth. Critical depth is not computed all the time because it's kind of an expensive calculation. You don't want to do it unless you really have to. So it does it under these conditions. If the water surface starts getting close to critical depth, then it'll compute it as well to make sure it's not going below critical depth. Or if the cross-section is at a boundary, at an external boundary, then it'll also compute critical depth. Or if the user requested the critical depth as an output, then in those cases it'll compute it. Critical depth is found by computing the minimum specific energy, and I'll show more about this in a second. There's two methods that are used in RAS. There's this parabolic method, which is very efficient, very fast, but sometimes that one can fail. And if that one fails, then it does this other method called the slicing method, which is more accurate, but it's more expensive. This is the parabolic method. So given 3 guesses, it fits a parabolic curve and then finds the lowest method on that curve. So this is the water surface here, and your critical depth is the point along this curve with the minimum total energy, right? And so the goal of this process is to find the point with the lowest energy here. And the parabolic method, what it does is it fits a parabolic curve to any 3 guesses. You need 3 guesses, and tries to find that point. Sometimes you have a curve that has little kinks in it, local minimum energy, and that can cause problem in computing the critical depth, the minimum flow. So you may fall in that little kink here and compute that. So that's when the splicing method does a better job, and the other parabolic method could fail. So the default method is the parabolic method. If it fails, it goes to the other one, but the user can change the critical depth method to always use the slicing method. It is more expensive. It'll automatically switch from parabolic to the other one in these cases. All right. So in certain cases, the energy equation doesn't work very well, like at low flow bridges or places with rapidly varied flow. And so you want to use the momentum equation. So we're going to introduce that here. And what this diagram is showing is a balance of all the forces for a volume of water inside of a channel. You have the friction force here. W is the weight of the water. And then these P's are the hydrostatic pressures. The theta is the slope of the river, and this is just the length of the segment of river. These are the bed elevations. And so this is forces equals mass acceleration in second law. And so if you balance all the forces, you go to the next slide, you get this equation, right? This is the momentum equation. So these are the hydrostatic pressures, the weight of the water, friction slope, and then this is mass, right? You have density here times acceleration, right? The change in velocity in the x direction. And so if we expand each one of those terms, we have the pressure term, the weight of the water, friction, and the mass times acceleration. I won't go into the details of like what every variable is. This is a momentum correction coefficient, this beta coefficient. So like I mentioned before, the momentum equation is used sometimes like at junctions, low flow at bridges, and then when you have mixed flow calculations, or the momentum equation is used to determine the location of the hydraulic jumps, right? And we'll talk more about mixed flow on Thursday afternoon. Cross-section spacing. The cross-section should be spaced in order to capture the changes in your geometry. So places where you have contractions or expansions, you need a finer resolution. Places where your slope changes, then you need cross-sections there. It's not just the geometry though, it's a function of your hydraulics. In places where your hydraulics are changing rapidly, you need more resolution in your cross-sections there. If you have a good feel for what your solution is going to be, then you can include that in your initial geometry from the beginning. But sometimes you have to run it once, kind of look at your results and then realize, oh, actually, my water surface is changing a lot in this area. I need to go add more cross-sections there. And if you plot things, sometimes it becomes more obvious, where you need more resolution if your water surface profile looks very jagged and that kind of thing. And it just takes experience to develop kind of a feel or intuition for where you need the cross-sections, where you need more resolution. One way of testing whether you have enough resolution is to actually increase the resolution and see if it affects your results. That's what we call grid convergence, and something that people should always be doing, but it's often overlooked. And you can do that fairly quickly with the cross-section interpolations, which we're going to introduce tomorrow morning. So you can lay out your cross-sections, and if you want to test whether that spacing is good enough, you can use the interpolations. It'll quickly add the cross-sections in between, and then you can test that very quickly and see if it changed your results. Bed slope obviously plays a very important role in the steady flow solution. So areas where you have steeper slopes require a smaller spacing. Places where you have a change in slope will require tighter spacing. Like mountain streams, you could have a cross-section spacing of like 50 feet or less, but for large rivers, very flat rivers, like the Missouri, Mississippi, you could have cross-section spacings that are larger than 1,000 feet. That's fine. One rule of thumb that is in the manual, I don't ever use it. And there's another one, Freed's equation. They're there if you want to use them. I don't generally use these. I just use kind of my intuition and one of my first bosses at HEC, what I would say, you never model something unless you know what the answer is already. That's kind of an exaggeration, right? But you have to picture what your solution is going to be, and if you don't, then you start with something rough, and then you iterate, you refine that. So I think that's a better approach than computing these things. When I mentioned this, right, the cross-section interpolation. When you're editing, when you're doing those tests, make copies of your geometry and create new plans so that you can compare them. Don't just work in one plan, edit the plan, rerun the plan, edit the plan, and rerun it, because you're not going to learn as much from that. It's nicer to create more plans and compare them, and you learn a lot more from that. You know, when I get projects from people, I know if they're a beginner or an advanced by like how much testing they've done before they come to me with something. You know, like I say, oh, the model doesn't run, and they made one mesh and they did one time step. You know, then I know they don't know what they're doing. But if they made a mesh and they tried lots of things, changed their spacing and tried different time steps, you know, looked at all those things, exhausted all of that, and it's still not running, then maybe it's a bug, you know. So compare and iterate. Yeah. Okay, limitations. So a big limitation is that it's the energy equation, right? It's not momentum equation, right? So it doesn't conserve momentum, it conserves energy. And in some situations, that energy equation doesn't do a great job. It's also steady flow. Often, steady flow gets used to model unsteady processes. Well, I mean, the natural rivers are always unsteady, but I think that's a big limitation of steady flow, of using it to model unsteady applications. So because of all the limitations of steady flow, sometimes and 1D, it takes a lot of skill to have a really good 1D steady flow model. Whereas a multidimensional model, as long as your boundary conditions and your geometry and all that is pretty good, then it kind of resolves all the physics for you. Whereas 1D steady and unsteady, it takes a lot more skill to overcome those limitations. You can overcome a lot of them, but it takes more work from your part. You know, the fact that it's 1D and so there's a velocity distribution across in a cross section. Well, you can get around that limitation by, you know, creating bins for conveyance along your cross section. But if you don't do those bins correctly, then it doesn't help you that much. But it does take skill to do that. It's 1D, so you have to know where the flow is going ahead of time, right? So if it's more of a multi-dimensional problem where it's the flow's kind of spilling over into an area, and the flow may go in various directions. That's not really a 1D problem, and 1D is not appropriate for that. Well, the limitations of 1D versus 2D versus 3D, right? You're basically assuming that the flow is mostly in one direction and one-dimensional. Yeah. Does anybody here have experience with the 2D RAS? I spent most of my career in multi-dimensional modeling. When I got into 1D, which, I mean, if I could say that, I found it very difficult because it takes a lot of skill. To do it well, to do it well takes skill. But is there any questions about how RAS computes the water surfaces for the 1D model? For subcritical flow, we'll get into mixed flow later in the week. But for subcritical flow, where does it start? The water surface elevation. Does it start downstream or upstream? Downstream, yeah. And are the water surfaces computed at cross sections or in between cross sections? At cross sections. The friction slope was that average friction slope. That was computed in between cross sections. So go back to the plot. All right. this is a cross-section, this is a cross-section. I should have explained it better. So starting from downstream you have a solution which includes, you know, your water depth, your water surface elevation, and a flow. You have a kinetic energy head, right? So this is your energy grade line. And you want to know what your water surface is up here. The first thing you do is you guess what it is based on this depth. You say, okay, I'm going to guess the depth is the same upstream, and compute conveyance, compute all of those things, then plug those values into my energy equation and compute a new water surface. And is this new water surface the same as the guessed one? And if it's not, then it'll keep converging. I mean, iterating. But so this this term, this H sub E, go to the next slide. That's what has the losses in it. The losses are this friction one and contraction and expansion. And when you see this bar, it's because it's an average value. This is an average between the two cross sections, right? And these sub indices are the cross section number, right?